Okay, so this is now lecture 3 of your module 1, okay, under the course Biomechanics. Now, you have here a picture of what we call UTM, or Universal Testing Machine. So say you have an object or a specimen, let's say a metal or any piece of material, let's say also maybe biological nature, let's say a tissue specimen, for example, so any material, okay? And you want to determine the mechanical properties of this material. So what you would do is to subject it under the universal testing machine. So the one in this picture is one example. So what it does is that the material will be subjected by to a series of loads or forces that will sort of stretch the material, okay? So in that case, we are able to find the stress and the corresponding strain using this equipment. And if we're going to plot stress in your y-axis and strain in your x-axis, okay, so we arrive at what we call the stress-strain curve. Okay. Now, so here's a representative stress-strain curve of a hypothetical material. Okay, and again, we use the engineering stress and engineering strain, or it's the same as nominal stress and nominal strain. Okay, as you can see here, you have here a blue region and a yellow region. Okay, so let's focus our attention first to the blue region. Okay, so this blue region corresponds, okay, which is, it's actually an area under this straight line here. And we already saw, okay, based on the previous lecture, that the slope of this straight line corresponds to the Young's modulus of the material, which has something to do with the stiffness of the material, okay? And you're seeing here a pretty stiff material, okay? The blue region is that region that corresponds or exhibits the what we call elastic behavior. So the blue region is the elastic behavior, and the orange or yellow region is the plastic region. Okay, so elastic and plastic. Okay, elastic and plastic. Okay. What do I mean? Because this region is a region where it's no longer elastic, but well, if you're going to combine these two regions, the plastic region and the elastic region, it gives you an idea on how tough, okay, the material is. Okay, you have a material, and if you elongate it long enough, okay, for example, like this one, okay, kapag in-elongate mo yung material mo, okay, so tumataas yung kanyang strain, tapos walang masyadong appreciable change in stress. So mayroong change in stress, tumataas. Kasi under this region here, habang tumataas yung stress, tumataas yung strain, and they are directly proportional. So we call that Hooke's law, right? Pero in this region, dun sa plastic region, habang okay, na-stretch yung material, okay, tumataas din naman at to a certain point yung stress, pero hindi na proportional yung kanilang relationship. Okay? Kasi nga, this is now your plastic behavior. Okay? It's not anymore elastic. When we say elastic kasi, kapag tinanggal mo yung stress, babalik siya sa dati na strain or dating position or elongation, right? While in your plastic region, it's not anymore the case. Okay, now if we consider again the blue region here, the area under this straight line is now what we call your resilience. Okay, resilience. So the slope of this line here is the Young's modulus, but the area is your resilience. Now, what will happen is that since your y-axis has a unit of uh, gigapascal or megapascal, and then your x-axis has values which are unitless, okay? So if you're going to take the area of this region here, again, this area is only the area under the straight line region, okay, and it corresponds to resilience. You will notice that the unit will still become gigapascal or megapascal, a unit of stress. And actually, this pascal or megapascal or gigapascal is also a unit of energy. Just to give an idea, Pascal is actually equivalent to joules per cubic meter. Okay? So if you multiply stress and strain to get the area here, okay, or if you determine the area through some numerical integration, for example, or simply considering this as a triangle, anyway, the dimension becomes, okay, that the unit will still be a unit of stress. And that unit of stress metric is Pascal. It's equivalent to joules per cubic meters. In other words, this area here, which is resilience, is a unit of energy. And actually, resilience is the energy that can be, the elastic energy that can be stored to the material. Okay? Now, this line here is linear, straight, up to a certain point called proportional limit. Okay, proportional limit. Okay, so that is the coordinates of the point kung saan nag-stop yung linearity dito sa straight line na to. Okay, how about your yield point? So this point now is your yield point. Okay. Now, what is yield point? Yield point is the point corresponding to when the material yields already. It begins to yield to plastic behavior. So it begins to transition from the elastic behavior to the plastic behavior. Yun yung yield point. And the stress corresponding to that yield point ay yung tinatawag na yield strength. Okay? So the point is the yield point, but the stress corresponding to that is the yield strength. And it usually correlates to the hardness of the material. Although in some cases, they more correlate the hardness of the material with what we call the ultimate tensile strength. But before we get to that, okay, how do we obtain the yield point or the yield strength? Okay, so all you have to do is to offset your strain here by 0.2%. So 0.2 is equivalent to 0.002. So that point of strain, okay, what you're going to do is to draw a parallel line, okay, a line parallel to this straight line here. Now, the point wherein that line, okay, which is shown here as a dotted line, so yung point kung saan kinokross na nung line na yan, yung curve dito sa taas, yun yung yield point. Okay, and again, yung yield point will correspond to your yield strength. Okay. Now, before I discuss the other properties here, let me first talk about ductility. So what is ductility? So ductility, it's the ability of a material to withstand tensile force. Okay? So meron kang material, you apply tensile force to the material, hinihila mo siya, kunyari, elongate mo siya through a certain force. Okay? And that material will elongate. Now, if that material was able to withstand that force, okay, inelongate mo siya ng inelongate, okay, without breaking the material, okay, kumbaga you're able to stretch the material into thin wire, okay, that means the material is ductile. And the reason why it's shown here na yung ductility ay, okay, yung extent ng strain, kasi nga, the more you are able to get a value for strain without breaking the material, the more ductile the material. Pero, Kunyari, ang curve mo na stress strain curve ay let's say ganito lang. Okay? Tapos at this point, nag-fracture na yung material. Okay? Compared to this curve, mas hindi ductile tong material na to. So this original curve that we have is more ductile compared to this curve that we have here. Kasi at point before even reaching 0.05, nag-break na yung material. So that's ductility. We usually use the term ductility kapag you are applying tensile force to the object. Pero kapag compressive force naman yung ina-apply mo, if you compress the material instead of elongating the material, we don't usually call it ductility, we call it malleability. It's the ability of a material to be hammered down into thin sheets, for example. Okay, but ductility and malleability, as far as the stress strain curve is concerned, they are the same. Okay, so the greater the extent of your strain before fracture, the greater the ductility or the malleability. Okay? Now, the opposite of these two, si ductility or malleability, the opposite is brittleness. Okay? So, this material here represented by this curve must be a brittle material. Okay, furthermore, the highest point in the stress strain curve is now what we call, okay, the corresponding stress is what we call your ultimate tensile strength. Okay, we call it also ultimate strength or ultimate stress. Okay, it's actually the maximum stress that the material can withstand. Okay, and lastly, you have here what we call your breaking strength. Yun yung stress corresponding to this point. Breaking strength is the strength at fracture. Yung material mo pag nag-fracture na, what is the corresponding stress? Yun yung breaking strength. Okay. So, kung napapansin nyo, mas mababa yung stress ni breaking strength kaysa ultimate tensile strength. Kasi, kahit na mababa siya, okay, na-stretch mo naman yung material up to this point. Okay? So, okay pa siya. Until, again, you have fractured the material here. Okay? Now, let's apply this into a very simple calculation. So I have here a question. Sauropods, are they too large? Were they too large to support their weight? So now the fact here is that land animals were thought to be size constrained by the strength of their bones. Okay, so let's take a look at this one. You have here Baluchitherium. I think it's one of the heaviest or largest mammals to ever walk on Earth, if not the largest. All right, and the size or the weight, rather, of this prehistoric animal is around 30 tons. Okay, so the question is, if the size of the bones constrain the ability or the maximum weight that can be supported, okay, could the foot bone support its weight na 30 tons? Given, for example, let's say that we know that the ultimate stress of the bone is around 100 megapascal. Okay, so you're also given that the diameter is 14 centimeters and the cross-sectional area based on that diameter is 151 times 10 raised to negative 4 square meters. So let's compute the mass that could be supported if the maximum strength is 100 megapascal. So it's a very simple calculation that the UTS or maximum stress is F over A. F is mg, the mass of the dinosaur or that mammal times the acceleration due to gravity, divided by the area, and the total area should be multiplied by 4, or the area of the foot should be multiplied by 4. There were 4 feet, no? Rearranging the equation, we solve for the mass. Okay, 4 times sigma max is this, 100 megapascal. Area is 151 times 10 raised to negative 4. G is 9.8, and you will obtain a mass of 698 kilograms. That's equivalent to 615.7 tons. And that's way above the mass of the mammal, no, na in question, yung Balocaidirium. Okay? 30 tons lang siya. So pwede. Okay? The weight can be supported by the bones or the strength of the bone.